Hello everyone, my name is Anu Anegi and today I'll be presenting my project called Smogcast, Real-Time Air Quality Classification and Multi-Step Forecasting. This project was completed as part of IE 6318 Data Mining and Analytics course at UT Arlington. Smogcast is an end-to-end data mining and deep learning system that transforms raw air quality sensor data into real-time public health insights. It classifies the air quality forecast and pollution trends for next 7 days to help citizens make informed decisions. Air pollution has become one of the most severe public health challenges in India due to rapid urbanization. Particulate matter such as PM 2.5 and PM10 frequently exceed safe levels, specifically in cities like Delhi and Kolkata. While real time monitoring exists, accessible predictable tools for citizens are pretty limited. Most systems only show like air quality without forecasting or recommendation. The goal of this project is to transform raw sensor data into actionable health advice using data mining and machine learning techniques. Smogcast has two main objectives. First, to classify current air quality into category like good, moderate, or severe. Second, to forecast pollution levels for next 7 days, allowing early warnings and better preparedness. The dataset here is from Kaggle called Air Quality Data in India. It contains over 7 lakh hourly observations across 26 cities between 2015 to 2020. The dataset includes wide range of pollutants, other the ones which I've mentioned before, that is PM 2.5 and PM10 is among them. Other than that, we have other nitrogen levels, sulfur levels, ozone, etc. There were like two key challenges here. First, the dataset had missing sensors for certain cities, meaning some pollutants had no readings at all. Second, there was a highly, like, it was a very highly imbalanced class dataset. Most days were labeled moderate, while severe pollution events were pretty rare, which is practically very good. But when we are talking in terms of data set, it becomes pretty tedious to work with it. So, in order to mitigate that, I built a pre-processing pipeline in order so before our model training can even begin. Here, I build it in four-stage process, like four stages of the pipeline. And the first stage was to impute, which where I followed a two-tiered strategy. First, filling missing values with local city median, then applying a zero fill safe approach to ensure that no city was dropped. Then step two was aggregation. Hourly readings were resampled into daily averages to remove short-term fluctuations and capture overall daily trends. Third comes the feature engineering. I created the lag features and 7 day rolling averages to compare temporal momentum in the pollution. I also applied cyclic time encoding using sine and cosine functions to help the model learn weekly and yearly patterns. For the step four, I did, and that was the last step of this pre-processing, that was scaling. All pollutants were log transformed to reduce the skewness and then scaled between 0 to 1 using min-max scaling. This pipeline transformed the messy original data into a normalized data set ready for machine learning. Moving ahead, first I did classification. For this task, I used CatBoost, which is a gradient boosting algorithm specifically optimized for categorical data. The model was trained to classify air quality index between good, moderate, poor, and severe. I trained the model over 500 iterations using multi-class objective function. To fix the imbalance between moderate and severe classes, I applied SMOT or synthetic minority oversampling technique. SMOT generates new synthetic samples for underrepresented classes, ensuring that the model learns patterns from the rare pollution events rather than just ignoring them. CatBoost has the ability to handle categorical city features natively, and it and its resistance to overfitting made it ideal for the structured data set, like in our context. For forecasting, I compared two deep learning architectures, one being bidirectional LSTM, the other being transformer. For the bidirectional LSTM model, the processes of the time sequences in both directions, like it checks from past to future and from future to past. The bidirectional structure allows the model to understand the context from entire time window instead of just previous values. Inside the each LSTM cell, gating mechanism decides which information to remember and which the target should forget and which to target actually. This helps the model retain meaningful long term pollution trends while ignoring short term random spikes. The transformer model, on the other hand, uses multi head self attention and positional encoding to capture relationships across the entire sequence. While transformers are powerful for large data sets, they can become unstable on smaller, noisier data, as I'll show in the results moving ahead. Here we have the experimental results the classification gives us. So the CatBoost model achieved an impressive global test accuracy of 92.39% with 94% precision for severe category. This means that the model very rarely misses the dangerous pollution event. It also handled borderline effectively, such as the differentiating between AQI values of 100 and 100 and 102, 100, all the ones which are on the borderline, by leveraging the temporal context from lag and rolling features. These results demonstrate that combining data quality, balance handling, and engineered temporal features leads to strong classification performance. Then we have our forecasting results also. In forecasting, bi-LSTM and transformer models performed well, both of them there, but there was a clear behavioral difference. Bi-LSTM produced smooth, realistic trends after that followed the overall pollution trajectory without overreacting to minor daily fluctuations. Transformer, in contrast, often produced spiky forecasts due to high sensitivity to noise and relatively small data set. And we have a similar kind of data set. Numerically, BioLSTM achieved the lower MAE, that is mean absolute error, typically ranging from 9 to 11, and lower root mean square error, that is RMSE also, we know it as, compared to Transformer, whose MAE ranged from 11 to 12. This confirmed that by LSTM gating's mechanism and bidirectional processing helped in capturing our graduate pollution transition more effectively as compared to transformer. Now we will move ahead to our plots and demonstration. So this is my deployment of my Smogcast app. It is an interactive real-time monitoring, and it consists of different plots which can help us and understand it better. So I'll just share that. So you just have to go here and select a city. For example, right now it is I was checking for Bangalore, so let's check again. Let's take Delhi. So it will change its stats based on the city you select. So here we have the metric results for Delhi. We can see the status is moderate. We can see the levels using the Gauss plot. We have 7 day forecast graphs. We can see the spiky transformer and smooth bi LSTM. We have the overall global performance, the global accuracy, and the class-wise precision and recall metrics. We even have additional daily trends of AQI. We can see there is a pattern in here. And then we have the composition of pollutants. We can see PM10 and PM2.5 being the lead here. Let's change the city and make it something like, let's do it Bhopal. It will change its results. So we can see good satisfied as the result label, and then we can even see the AQI levels coming down. We can see the graph has changed. We can see the new trend in AQI. The pollutant configuration has shifted a little bit, and then the graphs are also telling a different story here. So we can see like for each, it does it custom based on the city you select, and you get the metrics, making it more interactive. Here behind the scenes, we had already pre-trained the models with best weights, both for CatBoost and the neural network models. And then using Streamlit caching functions, we were able to retrieve results more faster, in a more faster way. And along with this, I was able to uh, host this on a cloud called Streamlit Cloud, as I made my full dashboard using Streamlit, which made it pretty easy for not involving many tedious back-end coding and all. Moving ahead, I'll go ahead with my conclusion. So, concluding for this, I would like to just say that Smogcast uh, has demonstrated how data mining and deep learning can turn raw environmental data into reliable public health insights. The project highlights that data quality and simplicity often outperforms complexity. Def- Despite being the simpler, the BioLSTM performed transformer and largely caused cleaner data effectively imputations and transformable feature engineering. In future, I plan to enhance the Smogcast by integrating real-time meteorological APIs, including wind speed, humidity, to capture external factors influencing the pollution dispersion. I also plan to fine-tune transformer hyperparameters and explore hybrid attention LSTM architectures to explore more further to improve the forecasting results. Thank you so much, and that should be the end of it.